Welcome back to the deep dive. Today we are actually cracking open the archives and rewinding the clock a bit to late 2019, which, I mean, it feels like an absolute lifetime ago in AI years, doesn't it?
Oh, it really does. I mean, that was the era of what I always call the arms race.
Right, because the prevailing narrative back then was incredibly simple. But it's just, bigger is better. You want a smarter model, just make it bigger. Throw more parameters at it.
Exactly. You had BERT, you had GPT-2, you had NVIDIA's Megatron. It was all about brute force scaling. Everyone was basically just trying to climb the leaderboard by stacking more layers and widening the hidden dimensions. And, it was effective, but it was also just it was heavy.
Yeah, it felt like if you wanted to build a faster race car, the entire industry strategy was just, well, put a bigger engine in it. Even if the engine was so heavy, like, crush the tires.
Yeah.
But today, we're looking at a paper that basically stepped back and said, hey, maybe we should look at aerodynamics instead.
That's a really great way to put it. The paper we're looking at is titled Albert, a light BERT for self-supervised learning of language representations. And it's a collaboration between researchers at Google Research and the Toyota Technological Institute at Chicago.
Right, and their mission here wasn't just to make a mini version for mobile phones, right? This wasn't just about shrinking a model so it fits in your pocket.
No, and I think that's the most common misconception with the name light BERT. They weren't trying to make a dumber, faster model. They were actually trying to solve a pretty massive paradox. They wanted a model that was significantly smaller in terms of its parameter count than the industry standard BERT, but, and here's the real kicker, they wanted it to perform better.
Which just sounds impossible on its face. Usually in deep learning, size equals intelligence. You essentially pay for smarts with RAM.
Precisely. But the researchers had hit a wall, a very hard physical wall. The paper dedicates a good chunk of the intro to explaining this memory wall.
Let's unpack that for everyone listening, because in 2019, we were starting to see models with hundreds of millions pushing into billions of parameters. What actually happens when you hit that wall?
Well, the most obvious thing is you literally just run out of GPU or TPU memory. You get an out-of-memory error. The model is just too fat to fit on the silicon chip. But the paper points out a more subtle and honestly arguably more annoying problem, which is communication overhead.
Communication overhead.
Yeah. So when your model is that incredibly massive, you can't train it on just one machine anymore. You have to distribute it across a cluster. But now you have these massive, distinct blocks of parameters that have to be perfectly synchronized across all these different servers. The gradients, the learning signals, they literally have to travel through the wires.
So the physical speed of light basically becomes
Your enemy.
Yeah.
Exactly. The more parameters you have, the more data you have to shove through those network cables every single time the model updates itself. It slows the training process down to an absolute crawl. So the Albert team asked a really fundamental question. They asked, is having better NLP models synonymous with having larger models?
They were challenging the absolute core assumption of the entire industry.
They really were. They wanted to see if they could decouple size from performance entirely. Like, if they could make the model lighter on parameters, but somehow denser in actual intelligence.
Okay, so let's get into the architecture of how they actually pulled that off. Because putting a massive AI model on a diet without starving its brain sounds tricky. The paper outlines three main innovations, and the first one is a bit of a mouthful. It's factorized embedding parameterization.
It is definitely a mouthful, but the concept underneath it is actually really elegant once you break it down.
So break it down for us. How did the original BERT handle embeddings, and why was that such a problem?
So think about the vocabulary of the model. In BERT, you have a vocabulary of about 30,000 words, well, tokens really, but let's call them words. And then you have the hidden layer size, which is the internal brain of the model, where all the complex processing actually happens.
Okay, I'm with you. 30,000 words and then a brain.
Right. Now, in the original BERT design, the size of the word embedding, which is the mathematical vector that represents a word like apple or dog, was tied directly to the size of that hidden layer. So let's call the embedding size E and the hidden size H. In BERT, E always equaled H.
So if I want a really smart brain, like a really big H, I have to have really big, complex definitions for every single word in my dictionary.
Exactly, and that is horribly inefficient. The paper makes a very smart distinction between context-independent representations and context-dependent ones.
Okay, what's the difference there?
So context-independent is basically just the static dictionary definition. Like, the word bank means a financial building or the side of a river. That's static. It doesn't really change. That's your embedding. But context-dependent, that's what the hidden layers do. They have to figure out what bank means in this specific sentence you're reading right now. That requires a lot of capacity. It needs to be highly complex.
So logically, the brain, the H part, needs to be huge, but the dictionary, the E part, can be pretty simple.
Spot on. But because BERT tied them tightly together, if you wanted to scale those hidden layers up to, say, 4,000 neurons to get a smarter model, your embedding matrix just exploded in size. You'd suddenly have a 30,000 by 4,000 matrix. That's over 100 million parameters just dedicated to the dictionary. And the kicker is, those parameters are highly sparse. They're rarely updated during training. It's just dead weight.
So how does Albert fix this? How does the factorization part actually work?
They just cut the link. They untied them. They decomposed that one massive matrix into two much smaller ones. Instead of projecting the word directly into the massive hidden layer H, they project it into a small, tight embedding space E first.
Like a bottleneck.
Exactly like a bottleneck. Say just 128 dimensions. Small, compact, highly efficient. And then they project that 128-dimensional vector up into the massive hidden layer space.
Oh, I see. So it's like a two-step elevator. You take one from the ground floor to the mezzanine, and then another from the mezzanine up to the penthouse.
That's a perfect analogy.
Yeah.
Mathematically, instead of V times H, you now have V times E plus E times H. And by doing this, they completely separated the vocabulary size from the model's overall complexity.
Which means they could make the hidden layers, the actual brain of the thing, as massive as they wanted without the embedding matrix just eating up all the available RAM.
Precisely. And the paper notes that they experimented heavily with this. They found that an embedding size of 128 was really the sweet spot. Even when they made the hidden layers absolutely huge, increasing the embedding size beyond 128 didn't really help the performance at all. It was just wasted space.
That seems like such an obvious win in hindsight. Why wasn't everyone just doing that from the start?
You know how it is. Sometimes the default settings just stick until someone bothers to question them. BERT set the standard, and everyone basically just copied the architecture wholesale because it worked.
Fair enough. So that's innovation number one, the diet for the dictionary, essentially. But innovation number two. Honestly, when I read this part of the paper, I just stop and reread it. It feels a bit radical. Cross-layer parameter sharing.
Yeah, this is the defining feature of Albert. This is where the architecture really gets weird.
Okay, so just to set the baseline. In a normal transformer model like BERT, you have a stack of layers. Layer 1, Layer 2, all the way up to maybe Layer 12 or 24. And traditionally, each of those layers is a completely unique block of parameters. Layer 1 has its own weights, Layer 2 has a totally different set of weights.
Correct. They are completely distinct entities. Layer 12 has a completely different mathematical brain structure than Layer 1.
And Albert just throws that out the window.
Drastically. Albert proposes reusing the exact same parameters across all the layers.
Wait, let me just make sure I have this straight. Layer 1 and Layer 12 are using the exact same mathematical weights.
Yes. In the most aggressive setting, which actually became the default for Albert, they share all parameters. The feed-forward networks, the attention mechanisms, every single thing is shared.
My immediate reaction to that is just, doesn't that make the model dumber? I mean, if it's just looping through the exact same brain over and over again, how does it ever learn hierarchy? How does it go from identifying a basic noun in Layer 1 to understanding deep sarcasm in Layer 12 if the machinery doing the processing is literally identical?
That is the totally intuitive objection, right? It feels like it absolutely shouldn't work. It sounds like you're just running a washing machine cycle 12 times and expecting a different outcome. But you have to think of it this way. The parameters are exactly the same, yes, but the input being fed into them is completely different.
Because Layer 2 is reading the output of Layer 1.
Exactly. Layer 1 takes the raw basic embeddings, it processes them, creates a new representation, and passes that up to Layer 2. Now, Layer 2 takes that representation, which is already partially abstracted, and runs it through the same function again. So even though the machine itself hasn't changed at all, the data being processed is becoming increasingly refined with every pass.
Okay, I think I can see that. It's almost like folding steel to make a sword. You use the exact same hammer, the exact same anvil, but the metal gets stronger and more complex with every single fold because the material itself is changing.
That's a really good visual. In the field, we sometimes refer to this as a deep equilibrium model. But let's just look at the raw efficiency gain first. By doing this, an Albert large configuration ends up having about 18 times fewer parameters than BERT large.
18 times.
Yeah, we're talking roughly 18 million parameters versus 334 million. That is just a massive difference in the memory footprint.
But does the model actually behave differently? You mentioned equilibrium. Does reusing those weights change the sort of texture of how the model thinks?
It absolutely does. And the paper actually has some really cool visualizations on this exact point. They measured the mathematical properties of the embeddings as they moved up through the layers. In a standard BERT model, the embeddings tend to converge. They stabilize as they go up the stack.
Meaning layer 23 ends up looking a whole lot like layer 24.
Right. They sort of settle into a groove. But in Albert, because the parameters are shared, the representations actually oscillate.
Oscillate, like they bounce around.
Yeah, they bounce around. The solution space is very, very different. The vectors don't settle down in that same predictable way. And here's the real surprise, the researchers argue that this oscillation isn't a bug, it's a feature.
How so? That sounds unstable.
Well, they suggest that this massive parameter sharing acts as a huge form of regularization.
Regularization.
Right.
Okay, so that's usually about preventing the model from cheating or just memorizing the training data.
Exactly.
Correct.
Because the exact same weights have to work perfectly for layer 1 and layer 12, the model can't just memorize specific cheap tricks for specific layers. It's forced to find deep, generalizable rules that apply to language universally. It basically forces the model to find a much smoother, more robust solution to the problem.
So paradoxically, by restricting the model, by tying its hands and saying you only get one single set of weights, they forced it to learn better, more universal rules.
That's the theory. And practically speaking, it completely solves the memory wall we talked about earlier. You can now make the network as deep as you want. You can just add more layers without adding a single extra parameter to your memory footprint. You literally just run the loop a few more times.
That is incredibly clever. So we've got factorized embeddings, which is the diet, and cross-layer sharing, which is the recycling. That solves the hardware efficiency problem. But the intro promised us a model that was also better, like actually smarter. And that brings us to the third innovation, the training objective.
Right. Innovations 1 and 2 were all about the architecture. Innovation 3 is about the education. How do we actually teach this specific machine?
Now, the original BERT used something called next sentence prediction, or NSP, which is basically just asking the model, is this sentence the one that logically comes after that sentence?
Yes. And for a long time, the whole industry thought NSP was absolutely crucial. We thought, okay, to truly understand language, the model clearly needs to understand the relationship between two consecutive sentences. But the Albert team looked closely at the data and realized something really interesting. NSP is actually way too easy.
Too easy. How can understanding sentence relationships be too easy?
Because NSP conflates two totally different things. It conflates topic prediction with actual coherence.
Give me an example of that.
Okay, let's say I give you a sentence about ice hockey. The goalie blocked the shot. And then I give you a second sentence about making a cheese souffle. Whisk the egg whites until stiff.
Okay.
And I ask you, the human, do these two sentences go together?
Obviously not.
Right. But did you actually need to use any deep logic to figure that out? Did you need to understand grammar or narrative flow?
No, I just saw goalie in the first one and egg whites in the second one and knew the topics completely clashed.
Exactly. And the model was cheating in the exact same way. It was basically just doing keyword matching, hockey words versus cooking words. It wasn't actually learning coherence. It wasn't learning how a narrative flows logically from point A to point B. It was just checking to see if the general topics were the same.
Oh, wow. So Albert decides to make the test harder.
Much harder. They threw out NSP entirely and introduced a new task called SOP, sentence order prediction.
How does SOP work differently?
In SOP, the model is given two consecutive segments from the exact same document. So the underlying topic is guaranteed to be identical.
Ah, so goalie and puck are in both of the segments.
Right. The positive example is simply those two segments in the correct order, A then B. But the negative example is those exact same two segments but swapped, B then A.
Oh, that is much trickier.
It forces the model to actually read the text. To figure out which one comes first, it has to deeply understand cause and effect, temporal logic, and discourse structure. It can't just rely on topic matching anymore, because the topic is identical in both cases.
It's the difference between asking, are these two books from the same genre, versus asking, did page 50 logically come before page 51?
That is a perfect analogy. And the proof is really in the pudding here. The paper shows that a model trained purely on the old NSP task performs effectively at random guessing when you give it this new SOP task.
Wait, random guessing. That's actually kind of a scary thought for all those BERT models running in production back then. They didn't actually understand structural order at all.
They barely understood it. They were coasting on topic prediction. But the Albert model trained on SOP, it absolutely crushed both tasks because it learned the deeper structural logic, which naturally encompasses the shallower topic matching anyway.
So we've rebuilt the physical architecture for maximum efficiency, and we've significantly toughened up the training school. Let's look at the actual scoreboard. Did all this fancy engineering translate to legitimately better results?
It absolutely did. Albert established new state-of-the-art results across 3 major benchmarks at the time: GLUE, Squad 2.0, and RACE.
I really want to zoom in on race for a second because the paper highlights it specifically, and I think it's fascinating.
Yes, RACE is a great benchmark. It stands for Reading Comprehension from Examinations. It's actually a massive data set collected directly from English exams given to middle and high school students in China.
And why is that specific data set so important for testing in AI?
Because exam questions are explicitly designed by humans to test deep reasoning. They aren't just simple find the word in the text tasks. They require real inference and deduction. The paper notes that the original research on the race task reported machine accuracy at roughly 44.1%.
Which is failing. That's an F- on a middle school test.
It's basically random guessing. Now, the original BERT definitely improved on that, but Albert pushed it all the way to 89.4%.
That is a stunning improvement. That's essentially doubling the baseline performance.
It's a massive leap forward. And what's really telling is the direct comparison with BERT, an Albert X-large model, which, remember, despite being the extra large version of Albert, still only has 70% of the parameters of BERT large. It significantly outperformed BERT large across all these reasoning tasks.
So it's significantly smaller, but wildly smarter.
And faster.
Right, let's talk about the speed, because we mentioned that memory wall and communication overhead earlier.
Because of all that parameter sharing, there is vastly less data that needs to be synced across the servers during training. So Albert Large is about 1.7 times faster at iterating through the data than BERT Large. You train faster, you use a fraction of the memory, and you get vastly better results. It was basically a total win-win-win.
There was one more finding in the paper that I found really surprising. It was kind of tucked away towards the end in the additional training data and dropout effects section. And this honestly feels like another one of those, wait, what moments in the research.
Oh, the dropout discovery. Yes, this is fascinating, especially for the actual practitioners listening right now.
So just for our listeners who don't train neural nets for a living, dropout is usually considered an absolute necessity, right? Like a core safety feature.
It's standard practice. It is deep learning 101. Dropout is a technique where you literally just randomly turn off a certain percentage of the neurons during the training phase. It prevents the model from just memorizing the training data, which is what we call overfitting. It essentially forces the model to be robust and learn the underlying patterns.
It's like studying for an exam with some of the pages of your textbook randomly glued together, so you have to learn the broad concepts, rather than just perfectly memorizing the exact sentences.
Exactly. You almost always use dropout. It's a given. But the Albert team noticed something really weird happening. Even after training for 1 million steps, their model simply wasn't overfitting.
Which is strange because usually if you train a model that long, it starts to just memorize the data and completely stops learning general applicable rules.
Right. But their graphs showed that the training loss and the validation loss were just tracking together perfectly. The model stubbornly refused to overfit. So the researchers decided to do something completely heretical.
They just removed the safety rail entirely.
They turned dropout off. Completely removed it.
And what actually happened?
The performance actually improved.
That seems to go against literally everything we're taught about neural networks.
It goes against standard convolutional neural network theory, certainly. But the analysis here is that Albert's highly specific structure, specifically that cross-layer parameter sharing we talked about earlier, it inherently provides its own massive form of regularization.
Ah, I see. The architecture itself is the safety rail.
Exactly. Because the model is so intensely constrained by having to reuse its own brain over and over for every layer, it physically can't easily overfit. It simply doesn't have enough unique, free parameters to just memorize random noise. So adding dropout on top of that strict architecture was actually just hurting the signal. It was unnecessary damage.
That is absolutely fascinating. It really implies that the standard best practices aren't always best if you fundamentally change the underlying architecture of the system.
It's a very stark reminder that deep learning is still very much an empirical science. You can't just blindly copy-paste settings from BERT to Albert. You have to actively test your assumptions every time.
So let's try to bring this all together for everyone listening. We started with the bigger is better brick wall that everyone was hitting back in 2019. Albert proved that you could break through that wall, not by just blindly adding more bricks, but by completely redesigning a better building.
Exactly. Albert showed the whole community that parameter count is not the only proxy for intelligence. It proved that efficiency and deep intelligence aren't mutually exclusive goals. By factorizing embeddings and aggressively sharing parameters, they made the model incredibly efficient. And by using sentence order prediction, they made it deeply coherent.
It really is the ultimate lesson in working smarter, not harder. I mean, Albert X large beats BERT large with 30% fewer parameters. It's just a leaner, significantly meaner machine.
And it paved the way for so much of the efficient transformer research that came right after it. It proved that we don't just have to accept hardware memory bloat as some necessary evil of progress.
Before we sign off today, I want to leave everyone listening with a specific thought, basically building on that whole dropout discovery we just talked about.
Oh, go for it.
We saw that removing a standard, unquestioned industry safety rail dropout actually improved this model, simply because the underlying architecture had evolved. It really makes you wonder, as we look at the current generation of AI today, the massive LLMs, GPT-4, Gemini, all of them, what other standard assumptions or established best practices are we currently just holding on to out of habit that might actually be holding these new models back from their full potential?
That is the million-dollar question, isn't it? Just because it worked perfectly for BERT doesn't mean it works for whatever comes next.
Definitely something to chew on. Thank you for joining us on this deep dive into Albert.
Always a pleasure to be here.
Be sure to check the show notes for a link to the original paper, and we'll catch you on the next deep dive.